Hey guys, ready for another round? 20 questions today on RAG pipeline architecture, AI search index design, and MLflow and serving governance. 10-second timer per question, then the answer and a short explanation. Pause anywhere you want a longer think. Good luck. Keep your focus here. Question 1. Picture the scenario first. A generative AI engineer at Dunmore Financial has a model serving endpoint with inference tables enabled. During a routine storage migration, the data engineering team renamed the inference table and added 2 new columns to its schema to satisfy updated compliance requirements. The following day, the team discovers that no new requests have been logged since the migration completed. What is the most likely cause? Select 1. Review the answer choices on screen. The correct answer is option A. Both rename and schema change end logging permanently. Inference tables stop logging and become corrupted when the underlying table schema is changed or when the table is renamed after initial configuration. Both conditions occurred during this migration. The team renamed the table and added new columns. Databricks requires that the inference table name and schema remain unchanged after the endpoint is configured. Any modification to either breaks the logging pipeline. The 128 concurrent request limit governs how many simultaneous requests the endpoint can process at one time and does not affect logging behavior. This limit can also be increased if needed. The sampling underscore fraction parameter ranges from 0 to 1 and is a deliberate user configuration. It would not be silently reset to 0 by a storage migration operation. HTTP 200 responses are fully captured by inference tables when logging is functioning correctly. It is error responses such as 401, 403, 429, and 500 that may not be logged. Keep your focus here. Question 2. The condition is doing work. A generative AI engineer at Helix Health is deploying an LLM assistant for clinical staff at a healthcare organization. Regulatory requirements mandate that patient identifiers such as email addresses and social security numbers must never appear in model responses delivered to users. The system must reject the response entirely when such identifiers are detected rather than sanitize the output. Which AI gateway guardrail configuration should they apply? Select 1. Review the answer choices on screen. The correct answer is option A. Blocking rejects entirely. Redaction only masks the value. PII blocking mode rejects any request or response containing personally identifiable information, such as email addresses, SSNs, or phone numbers, ensuring that such data never reaches the end user. This directly satisfies the regulatory requirement for complete prevention rather than sanitization. PII detection with redaction mode replaces identified tokens with placeholders rather than failing the request, which sanitizes output rather than blocking it, and does not meet the requirement to prevent any PII containing response from being delivered. Safety filters address content categories such as hate speech, violence, and sexual content, and are not designed to detect structured identifiers like SSNs or email addresses. Rate limiting controls how many requests a user or group can send per unit of time and governs access volume, not the content of requests or responses. Alright, question 3. Check the condition before the service. A generative AI engineer at Northwind Analytics is registering a fine-tuned language model into the organization's centralized governance system. The team uses Unity Catalog for all data and ML assets, and wants the model to be discoverable, auditable, and shareable across multiple business units. What is the correct namespace format for a Unity Catalog registered model, and which registry URI does MLflow 3 use by default to route model registrations to Unity Catalog? Select 1. Review the answer choices on screen. The correct answer is option A. Two-level namespaces both look plausible. Check the MLflow 3 default. Unity Catalog enforces a three-level namespace, catalog, schema, and object name, for all managed assets including registered models, following the pattern catalog.schema.model_name. This structure enables cross-workspace discoverability, fine-grained access control at each namespace level, and full lineage tracking across teams and business units. In MLflow 3, the default registry URI is Databricks UC, which automatically routes model registrations to Unity Catalog rather than the legacy workspace model registry. The two-level schema.model_name format omits the catalog tier, which is required to uniquely identify the model in a multi-catalog environment and to resolve naming ambiguity across workspaces. The single-level model_name format belongs to the legacy workspace registry and does not support Unity Catalog governance features such as lineage, attribute-based access control, or cross-workspace sharing. The two-level catalog.model_name skips the schema tier, which is a required structural level in Unity Catalog's three-part namespace. This one hides two traps inside a single question. Let's pull them apart. Imagine you're filing a model like a document in a big filing cabinet. Unity Catalog's filing system has three drawers: catalog, schema, and model name. Skip any drawer and the system can't find your file. That three-level address, like prod.ml_team.churn_model, is not optional. The question also asks what MLflow 3 does by default. In MLflow 2, routing to Unity Catalog was an explicit opt-in step. MLflow 3 flipped that. Databricks UC is now the built-in default. Options B and D each get one thing right and one thing wrong. The exam rewards catching both conditions at once. Keep your focus here. Question 4. Let the constraints drive the choice. A generative AI engineer is optimizing a legal discovery RAG system that must retrieve all documents relevant to a litigation case from a large corpus. The legal team's primary concern is that no relevant document is missed during retrieval, even if some non-relevant documents are also returned. Which retrieval metric should the engineer prioritize when evaluating and tuning this system? Select one. Review the answer choices on screen. The correct answer is option A. NDCG and DCG rank well but miss the coverage question. Recall at K measures what fraction of all known relevant documents appear within the top K retrieved results, ranging from 0 to 1. When completeness is the critical requirement, as in legal discovery where missing a single relevant document can have serious legal consequences, recall at K is the correct primary metric. A higher recall means fewer relevant documents are missed, even if the retrieved set also includes some non-relevant results. NDCG at K rewards highly relevant documents appearing near the top of the ranking and penalizes them appearing lower, but it is a ranking quality metric that does not directly capture whether all relevant documents were found. DCG at 10 measures discounted cumulative gain using a relevance scale weighted by position and is valuable for evaluating ranking quality, but it similarly does not measure completeness of retrieval. Precision at K measures the opposite concern. It quantifies how many retrieved documents are actually relevant, which matters for result quality but does not address whether the retrieval missed any relevant documents entirely. Okay. Question 5. Identify the business need first. A generative AI engineer is building a RAG application for a retail operations team. The application must answer natural language questions about current inventory levels stored in a relational database, and also answer questions about product manuals stored as PDF documents. How should the two data sources be handled differently within the RAG pipeline? Select one. Review the answer choices on screen. The correct answer is option B. Two data types, two retrieval strategies, neither one alone works. Structured data stored in relational databases is best queried using SQL, which applies precise filters, aggregations, and numeric comparisons that semantic search cannot reliably replicate. Unstructured PDF content is best handled through embedding and vector similarity search, which captures semantic meaning from prose. Passing both result sets to the LLM allows the model to reason across exact inventory facts and product knowledge in a single generation step. Embedding database rows as vectors loses the precision that makes relational data valuable and makes numeric filtering unreliable. Converting rows to plain text summaries discards the structured query capability and introduces summarization errors into inventory facts. Loading an entire database into a vector store and relying on metadata filters cannot perform the aggregations and exact numeric lookups that inventory queries require. First 5 revealed inference table fragility, PII blocking versus redaction, the 3-level UC namespace with MLflow 3's new default URI, recall at K for coverage, and the SQL plus vector hybrid pattern. OK. Question 6. Do not stop at the first match. A generative AI engineer at Meridian Financial is building a document search system for internal compliance reports. The company has a specialized domain-adapted embedding model hosted on an external inference cluster outside Databricks. The embeddings have already been computed, stored in a delta table alongside the source text chunks and metadata, and cannot be regenerated inside the Databricks workspace. The engineer needs to create an AI search index backed by this data. Which approach should they take? Select one. Review the answer choices on screen. The correct answer is option C. Re-embedding destroys the domain model's advantage entirely. A direct access index is purpose-built for scenarios where embeddings are generated and managed outside Databricks. The engineer calls create_direct_access_index and then upserts rows into the index programmatically, supplying the pre-computed vectors stored in the delta table. This preserves the domain-adapted embedding model's output without any recomputation. A delta sync index with a managed embedding model only works with models available through the Databricks Foundation Model API or Databricks hosted endpoints. An external inference cluster URL cannot be registered as a managed embedding source for this index type. Re-embedding with a Databricks hosted model would destroy the quality advantage of the specialized domain-adapted model and is unnecessary given that embeddings already exist. Direct access indexes cannot be created through the Databricks UI. The UI only supports delta sync index creation. Direct access indexes require the Python SDK or REST API. This one trips up a lot of people. Let's break down when to use each index type. Imagine your team trained a specialized embedding model on 5 years of compliance documents. It knows what Reg-T and Basel III mean in context. Now you want those embeddings in Databricks AI Search. Here's the fork in the road. A delta sync index auto-syncs with your source delta table, but its managed embedding step only works with Databricks hosted models. You can't just hand it a URL to your external cluster. Direct access is different. You own the vectors. You call create_direct_access_index, then upsert rows with your pre-computed embeddings. No re-embedding, no quality loss. One more trap. Delta sync can be created through the UI. Direct access indexes can't. You need the SDK. That's why option C is the only path that works here. Here we go. Question 7. This is a 2-step filter. A generative AI engineer flattened support ticket documents into a delta table with columns named _I.D.apostrophe, ticket_text, category, and submitted_date, then attempts to create a delta sync index on the table. The index creation fails immediately. What is the most likely cause and resolution? Select one. Review the answer choices on screen. The correct answer is option C. One reserved name in the source table kills creation. The column name _i.d is reserved within Databricks AI search and cannot be present in the source delta table used to create a delta sync index. When the source table contains a column with this reserved name, index creation fails immediately. The resolution is to rename the column to any non-reserved name before attempting to create the index. Timestamp and date columns are fully supported data types in delta tables and do not cause index creation to fail. Filterable metadata fields do require declaration at index creation time, but omitting them results in a configuration limitation rather than an outright creation failure. There is no minimum row count prerequisite for creating a delta sync index. Here we go. Question 8. Choose for this case, not every case. A generative AI engineer at Litware is building a RAG application for a retail analytics team. Users ask questions such as what was the total revenue by region last quarter. The relevant data lives in relational tables for orders, products, and customers stored in a SQL-accessible database. How should the engineer integrate this structured data into the RAG pipeline? Select 1. Review the answer choices on screen. The correct answer is option A. SQL executes the aggregation, vectors find the semantics. Structured data in relational tables is best integrated into a RAG pipeline by querying it with SQL at retrieval time. This allows the system to execute precise aggregations such as summing revenue and grouping by region, which semantic vector search cannot perform over numeric data. Exporting tables to PDFs and chunking them destroys the relational structure and makes aggregations impossible. Pre-embedding every row enables key value style lookups, but cannot execute sum, count, or group by operations that analytical questions require. A delta sync index synchronizes delta table changes into AI search for vector similarity search, but similarity search still cannot compute numerical aggregations over structured records. Next up, question 9. Look for the constraint that matters. A generative AI engineer is debugging a RAG application that returns vague, generic answers. Tracing the pipeline, they confirm that the retrieval component is working correctly. Relevant document chunks are consistently returned for each user query. However, the LLM's responses do not incorporate the retrieved content and instead rely on its pre-training knowledge. Which component of the RAG pipeline should the engineer investigate first? Select 1. Review the answer choices on screen. The correct answer is option A. Retrieval confirmed fine, so look one step downstream. In a RAG pipeline, the augmentation step is responsible for combining retrieved context chunks with the user's original query into a unified prompt that is passed to the LLM for generation. If the LLM ignores retrieved content and relies solely on its pre-training knowledge, the most likely cause is a failure in this augmentation step, for example, retrieved chunks not being injected into the prompt template correctly, or the template structure making the context invisible or ambiguous to the model. Embedding dimension mismatches would cause retrieval to fail or return irrelevant results, but the scenario confirms retrieval is working correctly. AI search scoring affects which documents are ranked and returned, yet the scenario confirms relevant chunks are consistently retrieved. Inference table logging is asynchronous and does not affect the real-time data flow between retrieval and generation. Next up, let's read question 10. A generative AI engineer at a consulting firm needs to integrate an OpenAI GPT-4o model into a Databricks-based application. The firm wants PII redaction and rate limiting applied to all calls to the external model, with usage tracked across multiple internal teams for cost attribution. Which Databricks feature supports this integration while providing these governance controls? Select 1. Review the answer choices on screen. The correct answer is option B. One feature handles PII, rate limits, and usage tracking together. Databricks AI Gateway is designed to proxy and govern calls to both Databricks hosted and external model providers including OpenAI, Anthropic, and Azure OpenAI. It provides configurable guardrails such as PII detection and redaction, safety filters, rate limiting enforced at the endpoint, user, or group level, and usage tracking for cost attribution across teams. This centralized governance approach eliminates the need for each application team to implement their own filtering and rate limiting logic. Foundation model APIs expose models that run on Databricks infrastructure and do not route traffic to external providers like OpenAI. A custom PyFunc wrapper can call OpenAI, but requires every team to maintain their own filtering code and provides no centralized governance, rate limiting, or cross-team usage tracking. Unity Catalog external locations manage cloud storage credential access for data workloads and are not a mechanism for proxying model API calls or enforcing inference-level guardrails. Questions 6 through 10. Direct access for external embeddings, the _I.D, reserved name gotcha, SQL for aggregations in RAG, the augmentation step as the generation breakpoint, and AI Gateway unifying guardrails for external providers. Next up, question 11. Map the qualifier to the answer. A generative AI engineer at Longview Systems is building an automated evaluation pipeline for an internal knowledge-based chatbot. They want the LLM judge to produce a structured reasoning trace, working through what the response says, what evidence supports it, and what gaps exist, before committing to a final quality score. This step-by-step reasoning is intended to reduce arbitrary and inconsistent ratings. Which evaluation methodology supports this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Reasoning trace before scoring. That phrase names the method. GEval with chain of thought is a single output evaluation technique that instructs the LLM judge to produce a step-by-step reasoning trace before assigning a numeric score. By externalizing the judge's reasoning process, this approach surfaces the criteria being applied and reduces variance from arbitrary or inconsistent scoring behavior. Pairwise comparison presents two candidate responses simultaneously and asks the judge to select the better one. It is designed for relative preference judgments between two outputs and does not generate a reasoning trace for a single response. Retrieval groundedness is a faithfulness metric that checks whether response claims are backed by retrieved documents, answering a specific question about factual support rather than overall response quality. Recall at K is a retrieval metric that measures document coverage and plays no role in evaluating or scoring generated responses. Let us keep moving. Question 12. Watch the tempting shortcut. A generative AI engineer at Brixton Research has generated embeddings for a biomedical document corpus using a specialized domain-adapted model running on an external GPU cluster. The pre-computed embedding vectors are stored in a delta table alongside the original text chunks and document metadata. The engineer wants to create a Databricks AI search index using these existing embeddings without recomputing them. Which index type and creation approach should they use? Select one. Review the answer choices on screen. The correct answer is option D. External GPU cluster cannot register as a managed embedding source. A direct access index is purpose-built for scenarios where embeddings are generated and managed outside Databricks. The engineer calls create_direct_access_index and then upserts rows into the index programmatically, supplying the pre-computed vectors stored in the delta table. This preserves the domain-adapted embedding model's output without any recomputation. A delta sync index with a managed embedding model only accepts models available through the Databricks Foundation Model API, or Databricks hosted endpoints, an external GPU cluster URL cannot be registered as a managed embedding source for this index type. Re-embedding with a Databricks hosted model would destroy the quality advantage of the specialized domain-adapted model and is unnecessary given that embeddings already exist. Direct access indexes cannot be created through the Databricks UI. The UI only supports Delta Sync index creation. Direct access indexes require the Python SDK or REST API. Time for another one. Question 13 is up. Quick check. A generative AI engineer deployed a provisioned throughput model serving endpoint for a customer service chatbot. The product team wants to analyze patterns in user queries and identify common failure modes in model responses over time, without building any custom logging infrastructure. Which native Databricks feature should they enable on the endpoint? Select one. Review the answer choices on screen. The correct answer is option B. 0 custom code, 0 Kafka, 1 toggle on the endpoint. Inference tables are a native model serving feature that automatically logs all incoming requests and outgoing responses to a Unity Catalog Delta table with no custom infrastructure required. The table is Databricks managed, queryable immediately with SQL or notebooks, and integrates with the existing Unity Catalog governance model, making it the zero operational overhead solution for capturing the full content of inference traffic. A Kafka stream requires provisioning and maintaining an external streaming infrastructure component, adding significant operational complexity. Adding a logging utility to the application code introduces a maintenance dependency in application logic and requires code changes for every application using the endpoint. A nightly batch job on system tables surfaces aggregate metrics rather than the full content of individual request-response pairs needed to identify specific failure modes, and introduces a significant lag between when failures occur and when they can be investigated. Time for another one. Careful on question 14. This one has a trap. A generative AI engineer at Harborfield Technologies is tracking an MLflow training run for a custom text classification model. They must record the batch size used for training, the per epoch F1 score measured across 15 training epochs, and the name of the feature engineering branch that produced the training dataset. Which combination of MLflow logging calls correctly captures all three values? Select one. Review the answer choices on screen. The correct answer is option D. Each call maps to a specific data shape, don't swap them. MLflow provides three distinct mechanisms for recording run metadata, each matched to a specific kind of value. Parameters are static configuration values fixed before training begins. Batch size is a canonical hyperparameter that does not change once a run starts, and are written with MLflow.log_param. Parameter values are immutable after being set, which reflects their role as fixed inputs to the run. Metrics are numeric values that can evolve throughout training and support an optional step index, making per epoch F1 score a natural fit from MLflow.log_metric. The step index lets MLflow render step index time series as training curves in the UI, enabling epoch-level diagnosis of model behavior. Tags are free-form string annotations that attach contextual information such as branch names, dataset identifiers, or team labels to a run, and are written with MLflow.set_tag. Recording batch size as a metric misrepresents a fixed configuration value as a time-varying measurement and prevents filtering runs by their training configuration. Tracking per epoch F1 score as a parameter loses the step-by-step progression that makes training curves useful, since parameter values cannot be updated with a step index. Storing a branch name as an artifact saves an opaque file blob rather than a structured, queryable string value, eliminating the ability to filter and sort runs by branch in the MLflow UI or via the tracking API. Here's one to get right. MLflow's 3 logging calls are not interchangeable, and the exam knows it. Picture a training run with 3 things to record. 1 never changes, batch size 32, fixed before training starts. 1 evolves across 15 epochs, F1 score climbs from 0.61 to 0.84. 1 is just a label, the Git branch that built the dataset. MLflow has a different call for each. Fixed numbers go into log_param, immutable once set. Changing numbers go into log_metric with a step index. That's how MLflow draws training curves. String labels go into set_tag, searchable in the UI. The trap is batch size. It's a number, so you might reach for log_metric, but it never moves across steps. That makes it a param. The question rewards knowing what changes versus what stays fixed. Time for another one. Question 15. Prioritize the stated requirement. A generative AI engineer is building a RAG application over a corpus of lengthy technical service manuals. Initial testing shows that small retrieval chunks yield precise semantic matches, but the LLM's responses are often incomplete because the narrow context window lacks sufficient surrounding information to synthesize a full answer. Which chunking strategy best resolves this retrieval context trade-off? Select one. Review the answer choices on screen. The correct answer is option D. Small index, large LLM context, 2 sizes, 1 retrieval call. Parent-child retrieval resolves the tension between retrieval precision and generation context by maintaining 2 granularities. Small 512 token chunks are embedded and searched for accurate semantic matching, but the LLM receives their larger 2048 token parent segments, which supply sufficient surrounding context for complete answers. This is a documented Databricks best practice for scenarios where precise retrieval and rich generation context are both required. Uniformly increasing chunk size to 2048 tokens supplies more context, but degrades retrieval precision, because larger chunks contain multiple topics and match queries less specifically. Semantic chunking produces coherent segments, but does not implement the small search large generate pattern needed here. Fixed-size chunking with overlap reduces boundary loss, but still passes only the small matched chunk to the LLM, leaving the context gap unresolved. Let's slow down on this one. The chunking trade-off is a classic RAG exam trap. Imagine you have a 500-page service manual. You want precise search, but you also want the LLM to answer fully. Here's the trap. Small chunks find the right paragraph, but the LLM only sees that paragraph. Large chunks give the LLM more context, but the search gets sloppy. Parent-child retrieval solves this with 2 layers. First, split the doc into small 512 token child chunks. Embed those for search. When a query hits, you find the best matching child chunk. Then you grab its parent, a 2048 token block with surrounding context. The LLM gets the big chunk. You searched small, you generated big. That's the trick the exam is testing. G-Evil's reasoning trace, the direct access index in a biomedical context, inference tables for zero infra logging, MLflow's 3 distinct logging primitives, and parent-child retrieval decoupling search granularity from generation context. Time for another one. Let's open question 16. A generative AI engineer at Northgate Capital is building an earnings analysis assistant that reads quarterly financial reports. Each report contains dense narrative text alongside tables with revenue figures, margin percentages, and year-over-year comparisons. The assistant must interpret numerical relationships within the tables and generate written summaries of key financial trends. Which foundation model API model is best suited for this use case? Select one. Review the answer choices on screen. The correct answer is option B. BGE Large produces vectors, not words. It cannot generate summaries. Llama 3.370B, Instruct is a large, instruction-tuned language model with a 128K context window and strong general reasoning capabilities, making it well-suited to processing mixed financial documents that combine narrative prose with structured numerical tables and producing coherent written summaries. BGE Large is an embedding model that converts text into fixed-dimensional vectors for retrieval and similarity search. It produces no text output whatsoever and cannot reason over financial figures or generate summaries of any kind. Code Llama 34B is purpose-built for generating and analyzing programming code across multiple languages and has no training advantage for financial table analysis or earnings report summarization. MPT-7B Instruct is a significantly smaller general-purpose model whose limited parameter count makes it less reliable for the complex multi-step numerical reasoning and synthesis that quarterly earnings analysis demands. Ready. Question 17. Anchor on the exact workload. A generative AI engineer is building a medical documentation assistant that retrieves context from patient clinical notes. Small, precise chunks improve similarity matching accuracy, but the LLM frequently produces incomplete answers because it lacks sufficient surrounding context from the note. The team wants a retrieval architecture that uses small chunks for accurate matching while supplying larger context segments to the LLM. Which approach should they implement? Select one. Review the answer choices on screen. The correct answer is option D. Same small search large answer pattern, recognize it faster now. Parent-child retrieval is the standard pattern for decoupling search precision from generation context. Small child chunks, typically around 512 tokens, are embedded and used for similarity matching because shorter, focused segments produce more accurate retrieval scores. When a child chunk is matched, the system retrieves its corresponding parent segment, typically around 2048 tokens, and passes that broader block to the LLM. This gives the model adequate surrounding context without degrading retrieval accuracy. Semantic chunking with single chunk retrieval optimizes boundary placement but still delivers only the matched chunk to the LLM, leaving the context insufficiency problem unsolved. Fixed size 1024 token chunks with 50% overlap doubles storage requirements and does not cleanly separate search granularity from generation context. Overlap helps preserve continuity at boundaries, but does not produce a coherent larger context block. Increasing model temperature affects response diversity, not the amount of retrieved context provided to the model. Ready. Let's handle question 18. Quick check. A generative AI engineer at Maplewood AI iterated on a summarization model over several weeks, logging evaluation scores, input/output traces, and production metrics against each run using MLflow logged models. Having identified the best performing run, they are ready to promote it to Unity Catalog as a model version for handoff to the production deployment team. What happens to all the performance data captured during development? Select one. Review the answer choices on screen. The correct answer is option B. Promotion carries all logged data to model version automatically. When a logged model is promoted to a Unity Catalog model version, the platform automatically surfaces all associated performance data, including logged metrics, parameters, and traces, on the model version page in Unity Catalog. This continuity means the production team can inspect the full development history without any manual data migration. Performance data is not deleted on promotion. The original experiment and its records remain intact in MLflow. The claim that data is locked inside the experiment and invisible from the model version page is incorrect. Promotion is specifically designed to carry that context forward. Manual export and reattachment is not required. The relationship between the logged model and its logged data is preserved automatically through the promotion workflow. Keep your focus here. Question 19. Compare the distractors carefully. A generative AI engineer is configuring a real-time pricing engine for a travel booking platform using Databricks Feature Serving. The feature spec must retrieve each user's pre-computed loyalty tier score from a published feature table and then apply an on-demand discount calculation before those values are served to the downstream pricing model. Which two feature spec components are required to configure this serving pipeline? Select 2. Review the answer choices on screen. The correct answers are option B and option D. Loyalty score lookup plus discount calculation. 2 steps, 2 components. Feature lookup retrieves pre-computed column values from a published online feature store table at serving time, which handles pulling the loyalty tier score for a given user identifier. Feature function applies an on-demand transformation or calculation during the serving call, which handles deriving the discount value from the retrieved loyalty score before the combined features reach the model. Together, these two components cover both the lookup and the transformation steps described. Online Feature Store is not a feature spec component in the Databricks Feature Serving SDK. It describes the underlying storage layer rather than a feature spec building block. Vector Search Retriever is an AI search concept for embedding-based retrieval and has no role in a feature serving pipeline. Delta Sync Index is an AI search concept for synchronizing a vector index with a delta table and is also not a feature spec component. Let's unpack this one. Knowing which feature spec building blocks do what is key to getting it right. Picture a travel booking site. The pricing model needs 2 things per user: a saved loyalty tier and a live discount. That's the feature spec's whole job. Feature lookup fetches the stored value from the online feature table. Say user ID 9912 has a loyalty score of 0.87. Feature lookup grabs that. Feature function then runs a fresh calculation on that score before it reaches the model. The distractors are real Databricks concepts, but they belong elsewhere. Online Feature Store describes storage, not a config component. Vector Search Retriever is for embedding search, not feature serving. Delta Sync Index is the same story. The exam rewards knowing both pipeline steps, the fetch and the transform. That's why B and D win. Keep your focus here. Question 20. Solve the situation, not the keyword. A generative AI engineer at Stellar AI built an internal knowledge assistant during a 3-month pilot using pay-per-token foundation model API endpoints. The product has been approved for enterprise rollout across 5,000 employees with sustained high query volume expected throughout the business day. Which serving configuration change should the engineer make before the production launch? Select 1. Review the answer choices on screen. The correct answer is option C. Pilot scale to 5,000 users, pay per token is the wrong tier now. Provisioned throughput is the recommended configuration for all production workloads with sustained high query volume. Configuring minimum and maximum tokens per second bounds guarantees allocated compute capacity, ensuring consistent low latency and reliable throughput for enterprise-scale traffic without the variability and potential throttling that pay-per-token endpoints can experience under sustained load. Pay-per-token endpoints are explicitly recommended during development and early experimentation because they require no capacity planning, but they are not designed for high-throughput production scenarios. Adding a caching layer reduces some redundant calls, but does not address the fundamental capacity and latency guarantees that provisioned throughput provides for sustained enterprise usage. Deploying separate pay-per-token endpoints per department does not change the underlying serving model, and managing dozens of endpoints increases operational complexity without solving the throughput problem. Routing through AI Gateway with a third-party pay-per-token provider introduces external dependencies and does not leverage Databricks' native provisioned throughput capacity. 3 takeaways from this session. First, direct access indexes require the Python SDK, The Databricks UI creates delta sync indexes only second. Parent-child retrieval embeds 512 token chunks for precision, but delivers 2048 token parents to the LLM third. AI Gateway centralizes PII blocking, rate limiting, and cross-team usage tracking for external provider models. These specific distinctions, which index type, which logging call, which serving tier, are exactly what the exam tests. If they're locking in, keep that momentum going.